Hi everybody, welcome to this class, Introduction to Artificial Intelligence and more specifically Neural Networks Basics. So my name is Tariq Dauda and this class should give you the theoretical basics to understand neural networks and how to train them. This class also comes with a Colab notebook where you'll find concrete examples on how to use all these different machine learning tools and how to apply all the theoretical knowledge that we will see during this class. When we talk about artificial intelligence, we talk about different types of applications. And probably the most known one is classification. It's a form of supervised learning. And supervised means that you have the data, but also have labels attached to the data. And in this case, it's a classification problem because we have pictures of dogs, pictures of cats, and the goal is to learn to differentiate these pictures. So when you show a new picture to the algorithm of a dog or a cat, the algorithm is able to classify it accordingly, saying that if it's a picture of a dog or a picture of a cat. The other type of applications that we often see is regression. So in the context of regression, you have a few data points here represented by the green dots, and the goal is to learn the underlying function that we don't know, here represented by the dotted line. And if you can do that, you could generate for any x, you can generate a realistic y. Another Another type of applications that we often see are the unsupervised learning applications. So in an unsupervised context, you have your inputs, but they're not associated to any labels or targets. And so you're working just on the inputs. And the goal is to discover meaningful structure in the data set. And the goal is usually for things like clustering and visualization. So we have an example here where this is a single cell data set of gene expression and each cell is represented by a dot. And originally each cell was represented by a vector of 20,000 values, one for each gene. But using an algorithm called t-SNE, we can reduce that to only 2 dimensions. And doing that, we can see the clusters and we can see the underlying structure of the data. Another type of applications that we will not see during this presentation, but that's very hot at the moment, is reinforcement learning. And this is more typically what people think of when they talk about artificial intelligence. And in a reinforcement learning context, you have one agent, and that agent has to perform a succession of actions, and in the end, you have a result that's either positive or negative. And the goal is to find the optimal succession of actions to maximize the positive results. Another type of applications that had a lot of success in the recent years is generative models. So for generative models, what you're trying to do is to learn the hidden or latent representation of something so that you can generate more of that thing. For example, here we have images of 2 people, and these people do not exist. These images have been generated by a generative adversarial network, or GAN for short. So what the GAN did in this specific context is that it has learned a hidden or latent representation of what a picture of a human face looks like, and then by sampling from that latent representation, you can generate new pictures of people that do not exist. Now we move to the data handling part. So this is an important part because you need to know how to basically store your information and how to encode it. So your data can be separated into 2 different categories. The first one is the continuous category. This would be like images or birth rate, for example, or temperatures, everything that takes a continuous value. And in that case, what you want to do is to reduce the range. If the range is too big in your values, you want to reduce it. So what you can do is simply use the log of the values. And you can also scale them between 0 and 1. So this is one method for doing it. You subtract the mean and divide by the max. Then you also have another category of data is called the discrete category, and this is everything like classes, categories, and everything that's basically discrete. And in that case, you just associate one unique ID or number to that category. For example, here you have different animals, and if each animal is associated to one single unique number. So the standard format is NumPy arrays if you're working with Python, and also pandas data frame. But underneath the pandas data frame, there are NumPy's arrays, so you always end up with NumPy arrays anyway. And if you have continuous values, you can cast them into float 32. Float 32 is precise enough. Most GPUs really like float 32, and it takes less space than float 64, which is a default for Python. When it comes to discrete values, you could use int 16 if you don't have too many of them. Int 16 is usually way more than enough. Otherwise, you can also use int 32. So let's move to supervised learning. So this is an example of a supervised learning data set. You have temperature, you have heart rate, and basically you have two types. This could be like two different diseases or two different conditions. You have the green one and the red one. So this is, you can see that on the left you have the inputs, and on the right you have the type, which is the label. An easy classification algorithm that's also very useful in many contexts is k nearest neighbors, KNN for short. So for KNN, you have your data set of green and red points, and over two dimensions here, heart rate and temperature. And if you get a new point and you want to assign a class to that new point and you don't know its class, basically you just plot it into your 2D space here, and you look at the class of, for example, k equal 3, its 3 nearest neighbors. And then it's a vote. So it's basically a majority vote. Here the point has 3, all 3 neighbors are green, so basically you would assign the green class to that point. KNN also allows us to introduce the concept of decision boundaries or space partitioning. And this is a concept, a general concept for all classification algorithms. And we can see that in the case of KNN, because if you have a new point here represented by the gray points that you have on the figure, if you have a new point, the class given to that point is always defined by the k nearest neighbors of that point. And because of that behavior, you can see that the space is naturally partitioned into two. So you have a red space and a green space. And if the new point falls into the red space, it is assigned class red. And if it falls into the green space, it is assigned class green. So now we can move to artificial neural networks. So the good news about artificial neural networks is that the basic math is not very complicated. So you have probably all seen a model like this one. So you have x here and you have another variable z here. So, and you can see that if you want to model to basically predict the value of z from x, all you have to do is to multiply by 10. So this is your model, and then you find that this is how basic neural networks work. So you have your model here, and you decide that z can be represented by a w times x, and then the goal is to find the best value for w, and just by looking at the data set here, you can see that the best value for w is 10. So this is like a slightly more complicated example. So here, instead of representing z by w times x, represented by w times x plus b, that we call bias usually in machine learning. And we can see that basically the goal here is to find a good value for w and a good value for b. And we just by looking at data set, we can see that the best values is 10 for w and 3 for b. So this algorithm basically is what is usually called linear regression. And so z is represented by w times x plus b, and if you find the right w and the right b, basically you've completed your task, and that's it. That's a very basic neural network. And in a neural network context, this will be represented like this. So you have x as an input, and you have the output layer is y here. And you have between x and y, you have something that is called a weight or a parameter, w1 here, and you also have the bias here, b. So, and you can see that the representation, the mathematical representation is exactly the same. This is the graphical representation of a neural network. So this is like a very basic neural network, and once again, the goal is to find the right value for W1 and B. So now, which brings us to the most important question, which is how do we find W1 automatically? So the first thing that we need is something that is called a loss function. So you have your input x here, you have your neural network, and then the neural network has an output here y, but you know also the truth. This is in a classification context, so you know, for example, this is a purely supervised, and you know what the truth here is, and it is z. You know it because it's in your data set. And the first thing that you need is the loss function. The loss function is simply something that tells you how far the output of the neural network is from the truth. And one classical example here is mean squared error, which is simply y minus z squared, and you take the average of that. So how do we use that loss function? So the loss function tells us how far we are from the truth. But what we really want is not to know how far we are from the truth, but how to basically tune W1 so that the network gives us a value the next time that we show the network an input that's similar to that one, the network outputs a value that's closer to the truth. And for that, we use an algorithm that's really the cornerstone of modern machine learning, and that algorithm is called gradient descent. So the way gradient descent works is that you take your loss, here mean squared error of the output of your network and the truth z, and you derive it with respect to the weight w1. So this is very important. It's not the variable here is w1, not x. You derive with respect to w1. And the goal here is to find the place where the derivative is equals to 0, because that place means that you cannot improve w1 more. Basically, you find a local minima. It's like locally you can do better than that. So the goal here is to find a place where the derivative of the loss with respect to the weight is 0. So if you remember your courses on derivatives, you know that for example, in this case, it's going down. You can see that the curve is going down, so the derivative is basically negative. And in this case, the curve is going up, so the derivative is basically positive. So you can see it's very clear from this cartoon here that basically all you have to do is to go on the opposite, to basically go to the opposite side of the derivative. So if the derivative is positive, then you subtract something from the weight, from W1. But if the derivative is negative, then you add something to W1. And if you keep doing that, then you will eventually end up to that place where where the derivative is basically 0. So the algorithm is a little bit more complicated than that. Usually don't want to add or subtract the whole derivative from your weight. One reason is very simple, is that you can add or subtract too much. Like you can see here, you can just overshoot and then you miss completely the local minimum you were looking for. And so what we usually do is you have W1, instead of having W1 minus the derivative, what you do is W1 minus a learning rate times the derivative. And the learning rate is usually very small. It's like 0.001, 0.0001, etc. You get the idea. So a very, very small update. And if you tune it well, you are pretty much guaranteed to end up into a local minimum. So this is our second baby neural network. So this neural network has two input variables, and you can see it's not very different from the first one. Instead of having just one x, you have x1, x2, two neurons as input, and one neuron as output, which is y1. And between them, you have weights w1 and w2. I have removed the bias. The bias, it's a convention. We don't usually write the bias because we know it's always there and it just takes up space. So remember that when you see something like this, there's always a bias hiding, but it's not basically drawn in the cartoon. And the mathematical representation of that graphical neural network is simply y1 equals w1 x1 plus w2 x2. And once again, the goal is to find w1 and w2, which are our weights. So the third version of our baby neural network is two outputs. And if we have two outputs, then you can see it gets slightly more complicated. So each input neuron is connected to each output neuron, and but basically it's just two times the neural network we've seen in the previous slide. So y1 is simply w1 1 times x1 plus w2 2 times x2, and y2 is w2 1 x1 and w2 2 x2. So it's pretty much the same thing, and do not forget that there's a bias here hiding. It's not shown. But if you read papers, this is usually not how you'll see neural networks drawn. They usually represented mathematically using linear algebra. And so it's just like a quick reminder of how linear algebra works, like with the very basics, like how to multiply two vectors. So we have one vector here, column vector, and a row column, and it's simply row to column. So multiplying this by that is simply a f plus be plus cj plus dk, basically, and that gives us a value here, v. So for matrices, it's basically the same thing, where you just do it more times. So you have always row to columns, and then you end up with another matrix here. So A times E plus B times F plus C times G plus D times H gives us basically the first number here in your matrix, and you keep doing that, and then you end up with the resulting matrix. And the reason I'm showing you that is because this is basically how neural networks are usually represented everywhere. So you rarely see this nowadays. You're most likely to see this. So here the way you read it is like this vector, a big vector y that contains y1 and y2, and there's a big input vector x that contains x1 and x2, and in between them there's a matrix w that contains all the w's from w1 1 to w2 2, that has basically, it's by multiplying this w to x, you end up with the vector y here. So you can see that this representation is way more compact, and if you have a neural network with a hidden layer, you can see here, for example, we have x, and we don't have directly x is not multiplied by w1 to give y. We have an intermediate step here. We have what is called the hidden layer, and the hidden layer is just a layer that is not an input or an output. That's why it's called a hidden layer. And you can see that it's pretty much the same thing. So h, the hidden layer, is w1 times x, y is w2 times h, and therefore we can write y as being w2 times w1 times x. A quick note on tensors. I know that some people are scared of the term. Tensors has just become in machine learning a name for pretty much anything. So a number is a 0D tensor, a vector is a 1D tensor, a matrix is a 2D tensor, etc., etc. And tensors can have as many dimensions as needed. So now that we've looked at how neural networks basically work and how they are usually represented, we can go and to more details into the workflow on how we use and train our networks in real life. So usually what you have is a training phase, and then you have an evaluation phase where you assess the performances of the network on real life data, and if that evaluation is not successful, you go back to the training and then you redo that step. If it is successful, then you can bring your model to production. This evaluation step is, of course, crucial to identify problems, and one of the main problems that you have absolutely to identify is overfitting. So what overfitting is imagine here this represents your data set. So the red points represents your data set, and the dashed line here is basically the best approximation, the approximation that you should have found using your well-designed machine learning algorithm. And you present it with the gray points here, and they almost fit the line. It's perfect, so you get good results, like the right value for x is associated to the right value for y. And this is an example of overfitting. So overfitting is the network basically overdoing it. And you can see the difference between the second cartoon and the first one is that the line here, the dashed line, goes like in through every one of these red points. And so your error, basically your loss function on your training set here would be much better than in here. It will be 0 because every point here in your data set has for each x is associated to its perfect y. But you can see here it's not the case. And the reason why it's not the case is probably because there was some noise in the gathering, like there's always noise in the data. But the problem here is that if the network overdoes it, then you have no guarantee that you will get good values for inputs that the network hasn't seen basically during the training. So as you can see here, if we show the same gray points to network, we have completely off results. And this is something that this is something that we absolutely need to evaluate and to avoid when we train machine learning algorithms. So this is another representation of overfitting on classification. So we have our red points, and here we have our green points, and this is the good decision boundary that we should have found. But instead of that, we have this wiggly, weird decision boundary. That means that every point that's here, for example, that should have been classified as being red, will be classified as being green. So this model is completely wrong and completely unusable in real life. So how do we ensure that we were not overfitting, for example? And the answer is surprisingly easy. What you do is you take your data set and you cut it into two independent parts. So the first part will be the training set. You can take 80% of the data, for example, for that. And then you take a reserve set, it's called a test set, that is absolutely independent and do not overlap with the training set. It's like the model should never see any example from the test set during the training. And once you finish with your training, what you're going to do is you're going to evaluate the performances of your model, your final model on the test set. And the value you get on the test set is an estimation of how well your model will perform in a real life situation on data that it hasn't seen during training. Interestingly, if you were to plot your loss on both the train and the test sets over time, you will see something like this. So the loss on the training set keeps going lower and lower and lower, converging towards zero. But at a certain point, same thing goes for a test set, but at a certain point, your loss on the test set will start going up. And that is the point where basically around that point of reflection, the model stopped generalizing and starts learning by heart. And basically, this is the point of reflection represents the moment where the network started to overfit. So there's a first regularization method. It's called early stopping, and basically with early stopping is that you just stop at that point of reflection. So here the question is, does that fix the problem? And the answer is no. And the reason why this doesn't solve the problem is because the point of reflection that you will choose on a specific test set is dependent on the test set. So it is the test set, because you have used the test set to stop your training. The test set, it has now been used to basically optimize the training. So it's no longer a test set, and so this approach is not valid. What you should do in that case, if you want to implement, so what you should do instead is take another set, a validation set, and use that validation set to decide when you should stop training. So this is a proper method of optimizing the early stopping, because in that case, the time when you stop has not been optimized on the test set, has been optimized on a different set. So your data set, now the data splitting would now look like something like this. So you can take, for example, 60% of the data for training only, and then you keep 20% of the data for the choice of hyperparameters. And this could be like when you stop for early stopping, but for a deep neural network, it could be anything like the learning rate or the number of layers or any one of these hyperparameters. And then you also have the test set that's reserved and that has not been used either for training or for the choice of hyperparameters. And the results that concerns you, the results you output, the results um, that you're really concerned with, are always the results on the test set, because they measure the performance for the model on examples that the network has never seen before. Another strategy that you can implement if you don't have enough data is, instead of having a specific validation set, what you can do is you use a five-fold or ten-fold, x-fold cross validation. This is a representation of five-fold cross validation. So what's happening here is that you will separate your training data into five folds. You would train on four and test on one. On validate on one, and you would do that 5 times. That way, you find your best hyperparameters, and then you next test your model on the reserved test set that has nothing to do with either the validation set or the training set. There are other regularizations. Here I'm defining regularization loosely as anything that limits the network capacity, because the reason why we had such problem with our decision, we have such a problem with our decision boundary here, is because there's the weights were given, for example, too much freedom. so they could flex too much. And there's a few things that you can do to limit that. So the first method that I'm showing you here for preventing overfitting is called L1 regularization. And basically what you do is you add something to the loss. And so you add a coefficient here, like it's this one, like usually it's a very small coefficient, and then you multiply it by the absolute value of the weights. So with L1 regularization, it works a little bit like friction because of that quantity that you're adding that's multiplied by the absolute value of the weights. This quantity, this new quantity, is never equals to zero. So what that means is that you always have some kind of friction and some incentive for the network to drive basically all the weights to zero. So what will happen is that the network will, if you tune your hyperparameters well, your network will use the weights that it needs and then try to tune all the others to very small values. So the L1 regularization is a bit harsh because the weights tend to collapse over zero, and that can also create problems like, for example, neurons with value because their weights, their inferent weights go to zero, their value also goes to zero, and then you lose these neurons forever. So there's another regularization that more gentle for it's called L2 regularization, and it looks very much like L1 regularization. The only difference is that instead of adding the absolute values of the weights, what you add is the squared value of the weights. And that simple difference is actually a very big difference because what happens now is that, and this is just like to give you some kind of intuition, so it's obviously more complicated what's happening inside the network, but what's happening on an intuitive dimension is basically your weights start behaving more like a spring. So if they are too high, basically there's a strong incentive to bring basically the weight toward a smaller value. But if the value of the weight is very small, then basically the network doesn't care that much. So this is why the L2 regularization is usually considered as being more gentle than L1. So now we move into deeper neural networks. So a deep neural network is simply a normal neural network with a lot of hidden layers. That's basically what it is. And there's different kinds of deep neural network, but on the basic level, they're all the same. They just have a lot of hidden layers. And why are deep neural networks interesting is because they allow for a rich processing of the data. So for example, if you had images, you get your images at the basically a bunch of pixels at the as an input, and then you get, for example, your first layer might learn to represent contrast lines like simple black and white contrast lines, and then you can bring these contrast lines together into the next layer to make features like eyes and ears, and then at the end you get something that's able to combine this feature to recognize faces. And the way deep neural networks are trained is still using gradient descent, and but so what you do is you have the first thing is the forward pass, so you give inputs to the network, you get an output, you compare it to the truth using a loss, and then you back propagate, which means that you start updating the weights from the top to the bottom, and like basically in a sequential way, although it's not very sequential, but you can think of it as being sequential. So you start by updating the top layer, and then you go up until the end. And this is how you fine tune your weights in the network. So once again, they are represented basically this way, if you open up a paper or anything about neural networks, you would see them as vectors multiplied by matrices. You will never see a neuron anywhere. You just see basically linear algebra and matrices and vectors being multiplied. So an important concept in deep neural network is the non-linearity concept. And so for that, we need to introduce what a non-linearity is. So you have on the right, on the left, sorry, you see something that's very linear. So basically what linear means is that it conserves the relationship between points. There are things like scaling, rotation, etc. You can see that on the cartoon on the left. Basically the relationship between the points doesn't change. It just gets big. Like if you divide any x by any y, you always get a. So that basic relationship never changes. On the right side, on the other hand, you see a log function. And it's very obvious that the log function basically changes the relationship between the point between x and y. Basically, it bends the space, basically. And you can see that the points are closer on the y-axis than they are on the x-axis. And this is what the non-linearity does. And because of that aspect, because they can bend the space, basically non-linearity gives more flexibility to the network. So how are they used? Because so far we just seen like very linear network. You just multiply w1 by x1 and you get y1. So a nonlinearity is not way more complicated, just a function that to which you give w1 multiplied by x1. And this function is usually called the activation function, but sometimes also called simply the nonlinearity. And here you can find an example of why nonlinearity can be interesting. You have, for example, in that context of at the bottom, this context of classification, you can see that there's no way in which you could draw a line and perfectly separate the red and the blue part. However, if you use a nonlinearity here, I think it was sigmoid, then it morphs the space is bended, and now it's very easy to trace a line between the blue and the red. So basically you can take, what that means is that you add a nonlinearity, and then because of that nonlinearity, this classification becomes easy even for a very, very simple neural network. So some very common nonlinearities that have been historically used a lot. Sigmoid here, that goes between 0 and 1, and tan h that goes between -1 and 1. You can see they have very similar shapes. And so these are very interesting. They've been used a lot, but they have also a very big issue, a very big problem, and that problem is called saturation. So if you remember the beginning of the presentation, the way we fine-tune the weights is basically by computing the loss, and then after computing the loss, you derive each weight you derive the loss with respect to each one of the weights, and this is how you can basically fine-tune the weights. But here the problem we have with saturating nonlinearities is that their values at the extremes are they're very flat at the extremes. So here we have a presentation of tan h on the left. You can see that if you are at 1 or -1, the derivative is basically 0. So now the problem that we have is that we have two cases where the derivative is basically 0. The first one is you're very close to your target, and the second one is your neuron is just saturating. And because you cannot, in both cases, it's exactly the same thing for the network, the derivative is close to 0, then there's basically little update of parameters, and the learning basically stops. Because of that saturation problems, among others, people have moved to different kinds of non-linearities, and the most used one is probably ReLU, rectified linear unit. And ReLU is the simplest non-linearity you can think of. Basically, it's x equals y equals x unless x is below 0, and then in that case just output 0. And so that can be problematic on its own, because during the training some neurons can have a value driven basically to 0, and then they never come back during the whole training, and they're just dead, and they're unusable for the whole training. So to counter that, people have found other versions of ReLU. One of them is ReLU, and the difference between leaky ReLU and ReLU is simply that instead of outputting 0, you output AX, and AX is usually a small value, but big enough to prevent that death of neurons. So ReLU basically is very fast to compute. It's non-saturating, and it is pretty much what most people are using at the moment. So now we move into more theoretical aspects about information theory and loss functions, so that we're not stuck with just mean squared error. So one of the first concepts that I would like to talk about is the concept of surprise. So surprise is very important in this case. So imagine that I tell you that tomorrow, the probability that tomorrow is going to be a sunny day is 0.98. So if it's a sunny day, you won't be very much surprised. But if it's not a sunny day, if it's a very cloudy day, it means that me, the model, I am not very good at predicting where tomorrow is going to be sunny or not. There's something that I've missed. And that surprise, basically, is alerts you that there's some information that you don't totally get. And so you can conceptualize surprise as being simply 1 over the probability. Another very important concept is the concept of quantity of information. So the quantity of information contained in X can be simply conceptualized as the number of yes/no questions needed to find X, and that is basically log 2 of X. So to illustrate this concept of quantity of information, I'll go back to this game of yes/no questions we've all played at a certain time. So, does it fly? Yes. Does it has feathers? No. Has fur? Yes. So it's probably a bat. And so in that case, I had to answer 3 questions. When I answered yes, I put a 1. When I answered no, I put in a 0. And that gave me 101 in binary, which is 5 in decimal. So if I take the log 2 of bat, I get 2.3. If I take the ceiling of 2.3, I get 3. And we basically means that I had to answer 3 yes, no questions. So this is the quantity of information contained in that name bat. Basically, it's really roughly the number of yes, no questions. So now we can bring the 2 concepts together, and we can measure the quantity of information in surprise. So the log of surprise is simply the log of 1 over the probability, and the log of 1 over something is just minus log of that thing, so it's just like minus log of the probability. And that also allows us to basically compute the average quantity of surprise, and that is just log of, for every class, for example, that we have from I to n, the log of the probability for that class multiplied by the probability of that class, and that gives us the average of the quantity of surprise, and this is called the entropy. So why is entropy so important? For us, it is because of cross-entropy. So cross-entropy is a loss function that allows us to compare the distribution of probability that we have, the truth basically, that we have in our training set with the distribution outputted by the model here. So how we do that is very simple. What we do is we just have to replace log p of x by log q of x, with q being the distribution of the outputs of the model. So you can see it's very similar in shape as the simple entropy. And the nice thing is that the solution is basically the cross entropy is the lowest when q of x and p of x are the same distribution. So using this loss function of cross entropy, we're able to fit closely the distribution of the inputs of the model, of the outputs of the model, to the distribution of uh, the, the outputs that the targets, the labels that we have in our training set. Another loss function that's very much used for classification is negative log likelihood. So negative log likelihood can be directly derived from cross entropy. So imagine you're in a classification context. You have to classify pictures of cats and dogs, and you know that if the image shows a cat, it doesn't show a dog, and if it shows a dog, it doesn't show a cat. There's no cat in the picture. So the probability for a picture showing a cat, the class cat for a picture showing a cat, is 1, and the probability for dog in a picture showing cat is 0. So if you use the cross entropy formula, in that case, basically you just left with only one class with probability p of x equals 1, and all the others equals 0, basically. So everything cancels out. And when everything cancels out, you just left with minus log of q of x for that class, the class of the target, and this loss function is called negative log likelihood. So finally, I'll talk about the output of neural network in a multi-class classification setup. So in that case, you don't have just cats and dogs, but you also have horses and pigs and dolphins and wallaroos, and each one of these different classes is associated to one single neuron, and for that reason, the output of the neural network has to be interpretable as a distribution of probability over the different classes. And so, for that to be true, the sum of the output has to be 1, and each one of these neurons, has to have a value between 0 and 1. And for that, we use a function called Softmax that you can see here. So this is the activation function that is usually used for multi-class classification setup. And it can be used with either losses that I've showed you. So if there's only one right answer, negative log likelihood. If there's more than one, it's cross entropy. So far we've only seen neural networks with fully connected layers. Layers where each neuron is connected to all the neurons of the layer above it, but also of the layer below it. Now we're going to move to another type of neural networks that are very much used, especially for image applications, and these are convolutional neural networks. The principle of CNNs is that they use small neural networks, such as the one we've seen earlier, with fully connected layers to scan the image. Each one of these neural networks is called a filter and only sees a small part of the image at a time. For example, a 3x3 pixel window. During training, these filters scan the image to learn small patterns, such as the ones that can fit in a 3x3 pixel window. And usually these filters are very small and very, very numerous. Deep CNNs usually have several layers of convolution, here in yellow. Each convolution layer has several filters, and the output of a filter is called a feature map. Each convolution layer learns patterns from the previous one, and this hierarchy allows CNNs to learn patterns, then patterns of patterns, and then patterns of patterns of patterns, etc. You get the idea. For classification applications, CNNs often end with fully connected layers in green here, such as the ones we've seen earlier in this presentation. You also notice that between the convolution layers, we have pooling layers here in red. These layers are used to subsample or reduce the size of the feature maps and also add some interesting properties to the network that we'll talk about later. Here we can see what the feature maps at every layer look like. The first layer of convolution only has three channels, red, green, and blue. At the next level, the number of channels increase as every feature map is now considered a new channel. As we go deeper in the network, the number of channels keep increasing and the representations become finer and finer. Because of the increase in number of channels, the number of parameters in a convolutional neural network can grow very large, requiring more memory and computation time. Historically, one way of limiting this growth is to use subsampling strategies such as max pooling. Max pooling partitions the feature maps and takes only the max for every partition. This reduces the number of inputs for the next layer and therefore the number of parameters in the network, but also gives some small resistance to small translations of the input. Finally, CNNs can also be used for sequences and have successfully been applied to the analysis of biological sequences. In this case, convolutions are usually 1D convolutions instead of the 2D convolutions typically used for images. We now move to recurrent neural networks. Recurrent neural networks, or RNNs for short, are typically used for sequences, temporal series, and inputs of different length. One of the main advantages of RNNs is that they keep a memory of the previous input, hidden states, or output, allowing them to tailor the output to the history of inputs received by the network. On the downside, RNNs can be trickier to train and could be subject to instabilities. For a neural network to be an RNN, it needs some kind of recurrence in other words, a loop. RNNs therefore roughly fall into two categories. The first one is networks that receive their previous output as input. In that case, the whole network is recurrent. The second case is network with hidden layers that receive their previous output. In this case, the recurrence only concerns a subset of the network. Historically, a very successful type of RNNs are LSTMs, or long short-term memory networks. LSTMs are easier to train than more traditional RNNs, and this is mainly due to their specific memory slot that's called a state. That state allows them to keep something in memory for an arbitrarily long period of time. And at each step of the LSTM training, the unit decides what to forget from the states, decides what to add to the states, then combine the states with the inputs and hidden representation, and then outputs the results, and then remembers the state for the next step. This is a general diagram of an LSTM unit. CT-1 is the state at the previous time, HT-1 is the hidden activation at the previous time, also the output of that unit at the previous time, and XT is the current input. We can see that LSTMs use two different types of nonlinearities, tanh and sigmoid, represented here by the sigma sign. We'll now move to analyzing each step of the LSTM process. The first step is to select what parts of the state should be forgotten depending on the current input and the previous hidden state, which is also the previous output. For that, the input and the previous output are combined and go through a layer with a sigmoid non-linearity. Because of the sigmoid, the output of that layer is a vector of scalars that are all between 0 and 1. That vector is then multiplied with the previous state vector to decide what part of it should be forgotten, basically, or remembered. Basically, a 0 implies that something must be completely forgotten and a 1 that it must be kept. The next step is to decide what part of the previous output and current input should be added to the state. The tan-h layer here scales the combination of the previous output with the current input between -1 and 1. It is then multiplied by a sigmoid layer like the previous one to decide which part of that combination of previous output and input should be kept, and the result is then added to the state. Finally, the state is scaled between -1 and 1 using a tan-h function, and the result is once again multiplied by the result of yet another sigmoid layer to decide which part of the states will become the next output. Here's once again the whole schema of an LSTM. You can notice that the first tan-h is a layer, while the second one is just an activation function. We now move to autoencoders. Autoencoders are classical unsupervised learning models and are often used for dimensionality reduction. A classical autoencoder is technically a standard deep fully connected network. However, instead of being trained to, for example, classify the inputs, an autoencoder is trained to reproduce it. Here, for example, the input is the image of a 4 and the desired output is the exact image of a 4. What makes autoencoders interesting is their bottleneck layer. Somewhere in the middle of the network, there is a layer with a dimensionality, the number of units in that layer, that is significantly smaller than the dimensionality of the input. If trained successfully, the bottleneck layer contains a compressed version of the input, and by using this approach, we can reduce the dimensionality of the input and get a more compact representation that is easier to analyze and visualize. Autoencoders come in different fashions. One of them is the denoising autoencoders, or DAEs. DAEs add noise to the input, and this could be normal noise or simply randomly masking some parts of the input. This strategy can improve generalization for the model and therefore enhance the quality of both the representation and the bottleneck layer. Arguably the most successful type of autoencoders and the most widely used for biological applications at the moment are variational autoencoders, or VAEs. In VAEs, the bottleneck layer is used to represent the parameters of a latent probability distribution, usually a normal distribution. Along with the standard cost of an autoencoder, that could be, for example, mean squared error, variational autoencoders add another term, which is the Kullback-Leibler divergence between the network's latent distribution and the chosen reference distribution. This distribution is usually a normal distribution centered on 0 with a standard variation of 1. The addition of this term forces the network to learn a latent representation distribution that is very close to the reference distribution. This improves the reconstruction quality and also the latent representation that is made more compact and easier to analyze. Finally, this also allows VAEs to be used as generative models. To use a VAE as a generative model, it is enough to sample from the reference latent distribution and give the result as input to the decoder, that section that is after the bottleneck. Because the network was trained to have a latent representation that closely resembles the reference distribution, this type of sampling will make the network generate random realistic outputs. Finally, autoencoders can be used for many different applications. They can be used to compress the input, but also as a pre-processing step to improve the generalization of other models, or as a dimensionality reduction tool for visualization. Now let's talk about convergence and the different alternatives to stochastic gradient descent. You are probably familiar with the local minima problem. Standard stochastic gradient descent, when you only use a random subset of example for each update, does not guarantee that you will not get stuck in a local minimum, for example here represented in blue, and never reach the green global minimum. However, for deep neural networks, the probability of ending up in a local minimum is very low. Because you have millions of parameters, the probability that you would be in a region of the space where derivatives for every one of these parameters is positive is extremely low. You are more likely to end up in a saddle point. Saddle points are regions of the space where the derivative is positive for some parameters and negative for others. In other words, you can still improve. But the derivatives can be so small, in other words, the surface can be almost flat, that it can be hard to find these directions of improvement. To solve this issue, researchers came up with different methods that all modify the standard stochastic gradient descent algorithm. Some of these methods use momentum, others use scaling of the gradient to force the exploration of regions that have not been explored before, and finally a third class combines both momentum and scaling. As seen in these videos, you can see how different methods are able to speed up convergence when compared to the standard stochastic gradient descent. One of the most widely used convergence algorithm is missing from this video and is called ADAM. I encourage you to research these different algorithms, and as this is beyond the scope of this course. Now some quick remarks on dimensionality reduction. You probably heard of PCA. PCA finds the main directions of variance and then projects the data onto them. However, as I briefly mentioned, there are other algorithms that you can use. One of them is t-SNE. The principle of t-SNE is that points that are likely to be close in the original higher dimensionality space are also likely to be close on the final lower dimensionality space. Another algorithm that is faster than t-SNE and gives also very good results is UMAP. I encourage you to try both of them, as dimensionality reduction is an important tool for machine learning. It can not only be used to get an intuitive understanding of your data, but it can also be used to get insight into your deep neural networks by using them, for example, to visualize the activations of your big hidden layers. Now to finish, I'll introduce some tools for machine learning. So for training, you can use NVIDIA's GPUs. If you need an interactive environment, you could use Jupyter Notebooks or Google Colab, which is Google free online version of Jupyter Notebooks. You can also train your models on different cloud services. Here I put Amazon Web Services, but there are other ones like OVH that you can use. For scientific computing, there's the classics NumPy, SciPy, Pandas, and also scikit-learn that is very, very useful for preprocessing your data. For visualizations, we have a lot of great libraries like Altair, Seaborn, Matplotlib, Wisdom, and ggplot2. For databases to store parts of your metadata and experiments, we have different solutions like AringoDB, Postgres, MySQL, and MongoDB. And finally, for the machine learning per se, we have TensorFlow, scikit-learn, Keras, and my personal favorite, PyTorch. So this ends this presentation. Thank you very much for listening to this course. I hope you enjoyed it, and I'm here if you have any questions.